Hello everyone and welcome back to the DSA course, and to this lecture we're going to be talking about AVL trees. We'll see how they work and let's go. So let's start. So first of all, we'll discuss what we had done earlier, which was balanced binary tree. So one of the disadvantage of binary search tree is that its height can be as large as n-1. So in the ideal case, the height is log of n, but at the worst case scenario, it is of the or it can be n-1. So the uh, time needed to perform insertion and deletion operations could be as large as order of n in the worst case. So since we always look at the worst case, order of n is not good enough for us. So in order to complete our insertions and deletions in order of log n time, we have AVL trees. So how do we do that? So we'll have to adjust our tree in a way such that the maximum height will be order of log n. So we want a tree with a smaller height. So a binary tree with n node has height at least order log n. So the minimum height would be log n, and we want that to be our case in our tree, in which we will do our insertion and deletions for the best time complexity. So our goal is to keep the height of a binary tree as order of log n, and such trees are called balanced binary trees, in which the height is of order log n, and some examples are AVL trees and red black trees. So in today's lecture we're going to be talking about AVL trees. So there are multiple types of binary trees. So in a full binary tree, in there full binary tree is one in which all nodes have either two children or none. So all the nodes have none of the nodes have a single child. So either it is a leaf node, in which case there are no children, or it is an internal node, in which case there will be two children. That is a full binary tree. Then in a complete binary tree, every level except possibly the last is completely filled, and all nodes in the last levels are as far left as possible. So as we had discussed in a previous lecture, we start filling from the top and from left to right. So at the top, root node would be 1. Then on the next level there could be maximum 2 possibilities, and then we will start filling from the left. So the left child will fill first, then the right child, then the left of the left child will be filled first, then the right of the left child, then the left of the right child, and the right of the right child. So in such a way we go height wise and then left to right. So we'll say whether this is a binary tree or not. So if that is a question, so in this case we can say that this is not a binary tree. Why? Because the order is not log n. So this is not a binary tree. The left subtree, which is this, from this root node to everything below this. So this is clearly much bigger than the right subtree, which is a single node. In the left tree we had 1, 2, 3, 4, 5. We had 5 nodes. In the right subtree we had a single node. So if this was balanced, we had 6 nodes. So we would have distributed 3 here and 3 here. Then it would be balanced. So this example, this is not a balanced tree. Sorry. So here is the example of balanced tree. So as you can see, the height of left subtree is equal to height of right subtree at each node. So when we look at the root node, height of left subtree is 2 and height of right subtree is also 2. When we look at this internal node, height of left and right subtree are both 1. Similarly for this, both are 1, and for the leaf nodes the height are 0, of course. So this is a balanced tree. Left subtree has the same depth as the right subtree. So what are the problems with the balanced trees? The perfectly balanced tree is far too strict of a restriction to place on a binary tree. So why is that the case? This is a perfect binary tree because we have to fill each and every node here. So this will have to be like if we had to fill, let's say, 5 nodes in our tree, then how could we do that? Sorry, let's say we have to fill 6 nodes in this case. Okay, then how will we do that? So we have one root node here, then we can fill one in the left, one in the right, then we can have 2 here, then this should be 5, and then finally we'll have to place a 6 node. So one child will have a single node, and this will lead to being not a perfectly balanced tree. So this will perfectly balanced tree can only occur in cases when each node is a geometric progression of 2 to the power. So at the first level, there are 2 to the power 0 nodes. At the second level, there are 2 to the power 1 nodes. At the third level, there are 2 to the power 2 nodes. So only in the addition of these powers, then only that case we can have a perfectly balanced tree. So what we have to do is we have to loosen the bounds. So somehow we have to allow uh, little bit of freedom in creating a tree, such that it would still be very near to log n and log n plus 1 or something like that. And in that case, our order would still be log of n, insertion deletion times, for very large values of n. So we could allow maybe on the left and right subtrees to differ by at most 1. So instead of being like exactly equal to, so the left subtree is exactly equal to right subtree, we can say that they can differ by at least 1. So if we discuss for the sixth case here, then if we just move this, the rightmost node here, then this will be perfectly valid, because for this node the difference is 1, and not, so difference is not, sorry, difference is 1, and then this is the most optimal way we can make a tree of 6 nodes. So that is perhaps what we can do. So and this is the solution which was proposed by these two Russian mathematicians, sorry, and by the name we name it AVL trees. So henceforth they're known as AVL trees. So these two are credited for AVL trees. So why should we use it? So while the AVL trees does not yield an average search in log n comparisons, we can achieve a solution in constant multiplied by log n times, which is pretty close to log n, which is as good as we can get. So and it is relatively easy to implement. All like it is still difficult, but it is relatively easy. So there are maximum of 2 modifications to a tree after an insert. So as we get to an overview of AVL tree, so AVL tree is a height balance tree. So for every node in a tree, the height of left and right subtrees differ by at most 1. So as we discussed earlier, we are allowing at most difference of 1 in the height of left and right subtree, and we will always have to rebalance the tree after each deletion or insertion. So after each update to a tree, we have to check the whether our tree satisfies the conditions for an AVL tree, and if it doesn't, we have to apply some changes to it, some modification to it, such that it becomes an AVL valid AVL tree. So AVL tree, let's look at this. An AVL tree is a binary search tree in which each node differ by at most 1. So this is uh, sorry, this one is an AVL tree. Why? Because if we look at each node, and the height of the left and right subtree differ by at most 1. So if we look at 5, then the height of left subtree is 3 and height of right subtree is 2. So 3 and 2 differ by 1. So this is fine. Then for this node 2, left is 1, right is 2. And similarly for 8, left is 1, right is 0. Then if we look at for each node, this condition is being this condition is happening. So we can say that this is a valid AVL tree. But for this tree on the right, at root 7, sorry, at node 7, we can see that the height of left subtree is 3, whereas the height of right subtree is only 1. So in this case, they are differing by 2. So we are not allowing a difference of 2. So we cannot say that this is an AVL tree. So AVL property is being violated here. So this is not an AVL tree. So insertion and deletions are handled in the same way as we did in an original binary search tree. A value is kept in each node which denotes the balanced condition of that node or the current height of the node, depending on the implementation. So we have to do some modification, as we said. If on inserting a node, let's say we are inserting a node C here, which according to a binary search tree rules has the minimum value. So according to that rule, it should go into the leftmost child, so which would be here. But in this case, we can clearly say that if we insert it simply here, then the height of left subtree for A would be 3 and height of right subtree would be 1, uh, uh, which would violate the condition for AVL trees. So this will not be an AVL tree. So we have to do some modification to this such that it becomes an AVL tree. So we call these things as rotations. So for this case, we have to perform a single rotation, and So there are single rotations and double rotation that we have to do, and for this case we have to perform a single rotation. So if you can imagine that we are moving everything to the right by one. So instead of making A the root node, we are making B the root node, and A is being pushed to the right child. And then the right child of B, which was here, we are making it as the left child of A. And then we are simply pushing BL and C to up one level. So if we look at this tree now, we can see that the values are according to the binary search tree values, like they're increasing from left to right, and AVL property is also being satisfied because the height is 2 and 2. So this was the case for insertion of node C, which was causing an imbalance. So we performed a single rotation, and this is the tree we obtained. So rotation. So since an insertion and deletion node involves addition and deleting of a single node, this can only increase and decrease the height of some tree by 1. So since we are only adding and deleting a node one at a time, we will only increase or decrease the height by 1. So here we are increasing the height by 1. So if the AVL tree property is violated so if we originally had an AVL tree and we add a node or add or delete a node, and the new tree is violating the AVL property, then the height difference between the left and right subtree would be differ by exactly 2, because we know that originally it had to be less than equal to 1, and since now after insertion and deletion uh, we are violating, then it had to be the case where now it is differing by exactly 2. So rotations will be applied at this case to x, because here we are saying that the heights of left subtree and right subtree of x are differing. So we have to apply rotations at x to restore the AVL property. So we'll look at insertion first. So first insert the new key as a new leaf node, just as an ordinary binary search tree. So as we just did normally in our binary search trees, we go from the root, we check whether it is less or the value is less or greater. Then if it is lower, then we go to the left subtree. If it is higher, then we go to the right subtree, and we go when we repeat this process until we get to a node which has value null, and then we insert our node there. So after doing that normally, then we trace the path from the new leaf node, with the node we just had, back towards the root. And for each node we encounter, so let's say this is the leaf node, then it will have a parent. Then we check for the AVL condition for that parent. Let's say it satisfies, then we go to the parent of that, and then we check for the condition again. Up we go. We do this all the way till we reach the root node. So we check the heights of left and right subtree for each parent, and we check whether the height is differing by at most 1 or not. So if it is differing by 1, then the AVL is being satisfied at that level. So we proceed to the parent of that node. And if it is not, then we have to perform a rotation for at that node, because if it is not differing by at most 1, it is differing by 2, in which case our AVL is not being followed. So we have to perform either a single rotation or a double rotation. So for insertion, if we perform a rotation at a single node, then we won't have to look back at the parents of that node. So we don't have to like we had in this case that we have to check for the parent of that node. So if we obtain a single case where our AVL property is not being followed, if we correct that, then everything would be correct. So we can just stop there. We don't have to keep going back parent by parent checking till up until the root node. So here we say let x be the node at which left and right subtree are differing by at most 1. So so the AVL property is being violated at node x. So if you assume the height of x is h plus 3, where h is any variable, any value, so there can be 4 cases which are possible. So we know that the left and right subtree would differ by exactly 2. So case number 1 would be the height of left x is h plus 2, and what will that mean? That the height of right would be h. Why is that? Because the if we the height of x was h plus 3, which included x itself. So 1 would be h plus 2, in which x will not be counted, and 1 would be h because they're differing by 2. We know that. So even within this case, where the height of left is h plus 2 and the height of right is h, there are two possible subcases. So in this case, the height of left is h plus 1. In this case, we have to perform a single rotation with left child. Or the height of right of left is h plus 1. So we know that the height of left is 2 greater. So if we just ignore the right for now, we come to the left tree. So we come to the h plus 1 level, and then we check whether the h plus 2th level is on the left child or the right. So if it is on the left, we perform single rotation to the left. So a single rotation, and if it is on the right, then we have to perform a double rotation with the left child. Then is the opposite case, in which the height of right is h plus 2 and the height of left is h. So in this case also, if it is right of right, then we have to perform a single rotation. But if it is left of right, then we have to perform double rotation. So if they are same, left of left, we have to or right of right, we have to perform single rotation. If they are different, right of left or left of right, then we have to perform a double rotation. So let's go through an example. So let's say we have to insert nodes in this particular order. So 3, 2, 1, 4, 5, 6, 7, 16, 15, 14. So first we have to insert 3. So since our tree is empty right now, we simply insert 3 and make this our root node. Then we have to insert 2. We insert it to the left because 2 is less than 3. We check AVL condition is being followed. Yes. So we stop it. And so our insertion is complete. Next we have to insert 1. So according to BST, 1 would be added to the left of 2. But in this case, when we check whether AVL is being satisfied, AVL property is being satisfied or not, our answer would be no, because at node 3, the height of left subtree is 2 and the height of right subtree is 0. So they are differing by 2. So and in this case, the case is of left of left. Left of left. So we have to perform a single rotation. So single rotation to the right, we are rotating everything towards the right. So our new subtree would look something like this. So 2 becomes our root node, 1 is to the left and 3 is to the right. So now this new tree at figure 4 is satisfying the AVL property. So insertion of 1 is complete. So next we go to insertion of 4. So we insert 4 to the right of 3 and AVL is being satisfied. So no problem. Then we insert 5. So here inserting 5 was by normal BST rules. We insert 5 to the right of 4. But again, AVL property is being violated here at node 3 because the right subtree has 2 height, whereas the left subtree has height 0. So again, this is the case for the right child has another child to the right. So we can see that the right child of 3 is 4 and the child of 4 is towards the right. So this is the case of right, and in this case we have to perform a single rotation to the left. So we are rotating everything towards the left at node 3. So 1 and 2 will not change. So, but everything at 3 we are performing it. So we rotate everything to the left. So it will look something like this, where 4 becomes the node node here, and then 3 to the left and 5 to the right. So at this point we had discussed that since we it was violating at 3 and we fixed it, so we do not have to check for 2 again, because it will be fixed for the entire tree. We know that, so we won't check for 2. We just simply go to the next step. So after 5 we'll have to insert 6. So inserting 6 would be like this, and now we check for the AVL property again. So at 6 there will be no problem, at 5 there will be no problem, at 4 there will be no problem, but at 2 there would be a problem because height of left is 1, height of right is 3. So again this is to the right of right, so we'll have to perform a single rotation. So it will look something like this at figure 9. Then we have to add 7. Then we are adding 7 here. This is right to right, so single rotation, and then we get this. So in this way, you can understand that what we are doing is we are applying rotations in cases where our AVL property is being violated, and thus a new modified tree uh, is abiding by the property of AVL trees. So after 7, we are adding 16, 15, 14. So let's say we are adding 16. Like 16 would be to the right of 7. So in this case, there is no problem. Then we are had to add 15. So 15 is to the left of 16. So this is the case where the left child of right child is uh, sorry the height of left is greater than the height of right of the right child. So this is the let's say come back to this. This is this case height of left and of right is h plus 1. So we have to perform the double rotation in this case, because if we simply rotate to the left, then we cannot do anything. So 16 would be at the top, then 7 would be at the left, but where would 15 go? So single rotation does not make sense, so we have to perform a double rotation. So in this case, we have to somehow bring 15 to the top and then 7 to the left, and 16 would stay at the right of 15. So this is the modification. This is a double rotation, and then finally we had to add 14. In this case, 14 would be to the right of 7, and in this case, our AVL property is being violated at the node 6. And again, we have to perform a double rotation. So because here you can see that uh, at 15, the height of left is 2 and height of right is 1. So height of left is 1 greater than height of right. So left of right is h plus 1. So we have to perform double rotation again. So this is much more complicated, and it will look something like this. So the left side will come to the top, so 7 comes to the top. The node which was here goes to the left of that, so 6 and 5 go to the left, and 15, 14, 16 will go right this. So 15 is here, 14 to the left of 15, and 16 to the right. So it can look a bit complicated. You have to get an understanding of how these rotations are working. So in this example, hopefully you are able to understand this example. So next comes the deletion part. So we have to delete a node x as an, so we initially delete the node normally as we do in original binary search tree, and then again we trace the path back from the node which we deleted back towards the root. So for each node x encountered, we check for the AVL property. So we check for the height of left subtree and the right subtree, and we check whether they differ by at most 1 or not. So if they are differing by at most 1, then AVL property is being satisfied at that node x. So we proceed to the parent of x, and we check again for the same condition, and if it is not being satisfied at node x, so they are differing by 2, then we have to apply a proper rotation at x. So again, 4 cases which would be which are similar to the cases we discussed in insertion. So there will be 4 cases deletion also. So for deletion, after we perform a rotation at x, we may have to perform a rotation at some ancestor of x. So we have to check for the parent of x also. So in insertion, we said that we could simply stop at the node x where we are modifying, but for deletion we have to check for the parents also. So that is something to keep in mind. So let's say this is an example. So we have to build an AVL tree for the following values. So this is an example. You can look 15, then 20 to the right, 24 to the right. In this case they are differing by 2, so we perform a right rotation. So 20 would be at top, 15 will come to the left, 24 come to the right, then 10 to the left, 13 to the right. So in this case at 15, properties being violated, so we have to perform a double rotation. So so double rotation. So in double rotation we are first changing this, so 13 comes to the top and 10 comes to the left, followed by a single rotation So it would be like this. So this entire step is a single double rotation. So double rotation consists of two single rotations. So first we did single rotation here. So 13 came to the top and 10 became its left child. And now you can see that this becomes the case of left. So, and then we can simply apply a single rotation towards the right clockwise, and then we can see that this is an AVL tree. So then 13 are added, then we are at 7, again it is being violated at 20, height of left is 3, height of right is 1. So we have to perform a single rotation. So 13 becomes the topmost, 7, 10 stay here, 15 comes to the right, 20, 24. Then we had to add, so after 7 we had to add 30, so 30 comes to the right, there's no problem in this case. Then but adding 36, sorry, so 36 goes to the right of 30, and we are our AVL property is being violated at 24. So right of right case, so single rotation anti-clockwise, so it will look like this. And then finally we have to perform at 25. So 25 comes here, and in this case the AVL property is being violated at 20. So, and this is a double rotation case. So first we apply a single rotation, so 24 comes to the top, 30 goes to the right, and then after that we perform a this becomes the case of right, and so we perform a single rotation anti-clockwise. So 24 comes to the top, 20, 15 drop to the left subtree, and 30, 25, 36 go to the right subtree. So here we can see that AVL property is being satisfied. So now let's say we had to remove 24 and 20 from AVL tree. So first of all, let's remove 24. So 24 was here. So on deleting, we get something like this. So we added the rightmost value of the left subtree, which was 20 in this case. So 20 became a node here, 15 came to the left, everything else remains the same. Then we delete it. So in this case, AVL tree is being AVL property is perfectly fine, so no problem. But we have to delete 20 now. So on deleting 20, again we are doing the max of the left subtree, which would be 15. So if we bring 15 to the top here, so in this case our AVL property is being violated at 15 because the height of left is 0, height of right is 2. So we have to perform a rotation. So on rotation we get something like this. So 30 comes to the top, 15 goes to the left, 25 will have to come to the right of 15, and 36 remains at the right. So it would look something like this. So if we check for AVL property now, 25 perfectly valid, at 15 valid, 36 valid, 7 valid, 10 valid, 30 valid, and 30 valid. So AVL property is being satisfied. So that was deletion. So we are only going to discuss we discussed how we inserted and deleted these nodes, so we won't code it in this course. The coding of AVL trees is beyond this course, so we just stop it here. This lecture was to help you understand that how these AVL trees work. So you have to understand how these work. So how using single rotations and double rotations we are modifying the tree at every insertion and deletion such that the maximum height is of the order 1.44 log n, as we discussed. So the height of left subtree and right subtree would differ by at most 1. So that was it for AVL trees. Hopefully you were able to understand it, and in the next lecture we'll discuss about heaps, binary heaps. So hope to see you in the next lecture. So wishing you happy learning, and goodbye. Thank you.